Welcome to the Darwin Severe Weather Analysis for Tuesday, November 25th, 2025. This morning's sounding reveals interesting tropical dynamics as we head into the late wet season build-up period. If you find this analysis helpful, please like and subscribe to support continued severe weather analysis. Let's examine this morning's 9 a.m. sounding from Darwin. Looking at the skew-t diagram, we see a classic tropical profile with abundant low-level moisture. The temperature and dew point lines are tightly packed near the surface, indicating a very moist boundary layer. There's a small area of pink shading showing modest CAPE of around 872 joules per kilogram, with the most unstable parcel reaching 1,291 joules per kilogram. The blue shaded area near the surface represents minimal convective inhibition of just 13 joules per kilogram, meaning there's essentially no CAP holding storms back. The lifting condensation level sits quite low at 639 meters above ground, which is typical for Darwin's humid tropical environment. With precipitable water at 54 millimeters, the atmosphere is absolutely saturated with moisture. However, deep layer wind shear is very weak at only 2.3 meters per second through the 0 to 6 kilometer layer, which will limit storm organization. Now let's look at the enhanced multi-parcel comparison to understand this afternoon's potential. The enhanced skew-t shows 3 different parcel paths, and we can see that heating the surface parcel creates a modest increase in instability. The surface-based parcel, shown in one of the dashed lines, reveals afternoon CAPE values reaching 1,429 joules per kilogram. The pink shaded area between the parcel path and the environmental temperature profile has expanded compared to this morning, showing the fuel building through the day. However, the environmental wind profile remains nearly unchanged, with deep layer shear staying extremely weak at just 2.5 meters per second. The supercell composite parameter remains minimal at 0.06, and the significant tornado parameter is effectively 0 at 0.01. What we are looking at here is a classic tropical pulse storm environment, plenty of moisture and moderate instability, but without the wind shear needed to organize storms into anything structured. If storms develop this afternoon, expect brief, disorganized cells with heavy rainfall as the primary threat. Looking ahead to tomorrow morning's machine learning forecast for late morning local time, the model predicts a similar tropical pattern continuing. CAPE values are expected around 972 joules per kilogram, with surface-based CAPE at 1,429 joules per kilogram. The lifting condensation level drops even lower to 688 meters above ground, maintaining that humid tropical character. Deep layer shear remains weak at 2.5 meters per second, keeping the supercell composite parameter at just 0.06. The environment will support disorganized pulse convection if triggered, with heavy rainfall the primary concern rather than severe weather. Tomorrow afternoon's forecast, valid for mid-afternoon local time, shows the pattern persisting through the diurnal cycle. The machine learning model predicts CAPE decreasing slightly to 853 joules per kilogram, with surface-based CAPE at 1,091 joules per kilogram. The lifting condensation level rises to 928 meters above ground as afternoon mixing occurs. Deep layer shear weakens further to just 2.2 meters per second, maintaining that disorganized storm mode. The lapse rate between 700 and 500 millibars sits at 4.8 degrees Celsius per kilometer, which is fairly modest. Tomorrow afternoon will feature similar conditions to today. If storms develop, expect brief, pulse-type cells with localized heavy rainfall. The lack of wind shear continues to preclude any organized severe weather threat. The multi-parameter evolution chart shows how conditions transform through the day and into tomorrow. Looking at the CAPE evolution, we see instability building from morning values around 800 joules per kilogram, peaking in the afternoon near 1,400, then maintaining similar levels into tomorrow. The deep layer shear trace remains nearly flat throughout the period, hovering between 2 and 3 meters per second, which explains why storm organization remains limited. Storm relative helicity stays minimal, barely registering above 0 throughout the forecast period. The supercell composite parameter line hugs the bottom of the chart, never exceeding 0.1. What this evolution tells us is that we have a persistent tropical pattern, plenty of moisture and moderate instability for storm fuel, but the missing ingredient is wind shear. Without that shear, storms will remain disorganized pulse cells rather than evolving into organized severe weather producers. The hodograph and wind profile paint a clear picture of the shear environment. Looking at the hodograph, we see the wind vectors form a very tight spiral near the origin, which indicates extremely weak directional and speed shear throughout the troposphere. From the surface up through 6 kilometers, winds barely change direction, remaining generally easterly to southeasterly at less than 10 knots. The right mover storm motion vector points toward the west-southwest, but with such weak environmental flow, any storms that develop will be nearly stationary. The 0 to 1 kilometer bulk shear is just 4.4 meters per second, and storm relative helicity in that layer is only 29 meters squared per second squared. These are far below the thresholds needed for supercell development. In practical terms, this wind profile supports only disorganized multicellular storms or isolated pulse cells, with no potential for rotating updrafts or organized severe weather structures. The Brunt-Väisälä frequency profile reveals the atmosphere's stability structure. Looking at the n-squared profile, we see near-neutral stability in the boundary layer up to about 1 kilometer, which is typical for the well-mixed tropical boundary layer. Between 1 and 3 kilometers, there's a modest stable layer where the profile shows positive values, representing where the trade wind inversion often sits in Darwin's tropical environment. Above that, the mid-troposphere shows near-neutral to slightly unstable stratification through the middle levels. There are no strong stable layers that would act as significant caps to convection. This profile supports the ease with which pulse storms can develop in this environment, but the lack of significant layering also means there's no mechanism to build up large-scale instability for more significant events. In summary, Darwin's atmosphere today and tomorrow features typical late build-up tropical conditions, abundant moisture, moderate instability, but critically lacking the wind shear needed for organized severe weather. If storms develop, expect brief, pulse-type cells with heavy rainfall and frequent lightning, but minimal severe weather threat. Always consult the Bureau of Meteorology for official forecasts and warnings. This analysis is provided by Distant Curve Remote Area Telecommunications. If you found this helpful, please like and subscribe to support continued severe weather coverage for remote Australia.